you see?
Yes.
Okay. Hi everyone. I'm Inseong, a PhD student from UOW under supervision of Attila and Peter. Today, I would like to talk about my recent research outcome titled Electronic Coupling, a significant contributor to electron transfer between similarly structured surface-bound porphyrins and cobalt complex electrolytes. So redox molecules are often attached to the electrode surface. By doing that, we can overcome like for example, mass transport limitations, and that makes like the better electronic coupling to the electrode. And in that case, there is an electron transfer from like donor species, another like redox molecule dissolved in electrolyte, to the like surface-bound acceptor molecule attached to the electrode surface. And the rate of this reaction is critically affected by the driving force, which is the energy difference between the donor and acceptor molecules. And when we increase the driving force, we can get like fast electron transfer rates. So people quite often change the electronic structure of the redox molecules to control the electron transfer rates. For example, in dye sensor solar cell, so people use cobalt complexes as a redox mediator, which is a donor molecule of this electron transfer. And by attaching some like substituent, for example, methyl, like alkyl groups or like some halogen type of simple groups, we can change the electronic structure so that it affects redox potential of this molecule and driving force for the reaction. So the rate between the electron transfer rate between this donor and acceptor molecule can be plotted as a function of delta G and fitted to the Markov theory of electron transfer. It shows a driving force dependent electron transfer rate. And there is an assumption in that case, for this practice, we need to assume that the electronic coupling, which is HDA in this equation, and the reorganization energy, which is lambda, don't change between these very similarly structured redox active molecules. So the tuning this electronic structure of the redox molecule is an like often used strategy to enhance electron transfer rates. But increasing the driving force doesn't always have the positive effect. In some systems, if you increase the driving force, that decreases actually the potential energy in the system. So it results in the loss of energy utilization. So in that case, probably we need other ways to control the electron transfer rates. So here is an like example of recent emerging strategy, which is structural effect on electron transfer rate. Here is an example. There are three different types of electron acceptor molecules attached to the electrode surface. And as you can see in the red circles, they have different structural moieties. And among those, one has three-dimensional structure, showed the fastest electron transfer rate measured by transient absorption spectroscopy. This is because of the better electronic coupling. So this work suggested that we can actually enhance electron transfer rate without increasing the driving force or with a very minimum increase in the driving force. So structural factor can also critically affect the electron transfer rate by changing the electronic coupling. So here's another example. Electron transfer can be like enhanced by 13 times using like by exploiting alkyl-alkyl chain intermolecular interaction at the same driving force between this like very long alkyl chain substituted cobalt complex and also alkyl chain substituted like surface bound molecules. So that makes the cobalt complex is trapped inside of the like acceptor molecular layer, so that it provides better coupling, hence better electron transfer rates. So we can think about other like molecular interaction because it's kind of very intriguing topic to enhance electron transfer rate. So we came up with electrostatic interaction because it is quite often used to like make the better coupling in the electron transfer system. So what we came up with this porphyrin because, like speaking of porphyrin, first of all, it is quite often attached to the electrode surface and act as a like redox active molecules. And it is possible to actually incorporating like metal ions into porphyrin, and that doesn't change like very huge the physical like dimension quite largely, so that we can change their redox potentials, but we can keep the physical dimension like quite same as before. So here, for example, if you insert zinc ions into the porphyrin cavity, we can change the redox potentials of the molecule by like 200 millivolt, but it doesn't like change the physical dimension that large. So that is the not only the consequence, but here you can see on the electrostatic potential map, by inserting like zinc ions into the porphyrin cavity, we can change the like electron density at the center of the porphyrin. So as compared to the zinc one, free base GD1, which doesn't have zinc ion incorporated into the porphyrin cavity, has higher electron density. So we set some hypothesis, which is that this difference in electron density may cause the like electronic coupling difference between the two donor and acceptor molecules, so that it might affect electron transfer rate. So these molecules are what we employed in this work. First of all, as I explained in the previous slide, we've got like a set of free base and zinc porphyrins, which is GD1 and 3GD1. And like for the like general trend, we employed another set of free base and zinc porphyrins, and they have different these anchoring groups and like solubilizing structures, so that they further shift the redox potentials of the porphyrin from the GD1 and 3GD1. And these four surface bound molecules are paired with 5 similarly structured cobalt complexes by substituting the ligand with some simple molecules. So this is important because we need to actually, in order to study the electronic coupling effect, we need to distinguish that effect from the driving force dependence, as I explained before. So we determined the redox potentials changed by the molecular structure using electrochemical method. Like first of all, we perform cyclic voltammetry for determining the cobalt electrolytes redox potentials by changing the substituents and the ligand structure, the redox potential shifts. And for the like surface bound porphyrin molecules, we perform differential pulse voltammetry. So the energy diagram on the right-hand side of the slide shows the redox potentials determined by these electrochemical methods, and they show the delta G out of these compounds covers 0.78 electron volt that allows us to study and it allows us to have a look at the electron transfer rate at this like wide range of delta G, so that we can distinguish some parameters from the other. So to determine the charge transfer rates, we employed transient absorption spectroscopy, and for this reaction to the like surface bound dimolecules from the donor electrolyte species, normally measured using like nanosecond time resolved transient absorption setup. So we first employed 10 nanosecond time resolved transient absorption setup to measure the electron transfer rate. However, what we found is we've got very steep decay with very indistinct initial signal plateau region that might imply that some of the transient absorption decay was missing. So we also employed another transient absorption setup, which is much faster, having 0.5 nanosecond time resolution that allows us to measure transient absorption decay signal from 1 nanosecond to 1 microsecond. So using these two measured curves by two different setups, but on the same sample, merged them into one smooth, nice curve, and then fit it to the stretched exponential function to get a charge the decay rate. And the measured decay rate can be like plotted as a function of delta G. So each point inside of this plot is like transient absorption decay rate using, for example, in this case, GD2 paired with 5 different cobalt mediators employed in this work. And this plot was fitted to the Marcus theory of electron transfer, the equation. So the outcome out of this fitting is electronic coupling, HDA, and the like reorganization energy. So we did the same for the other surface bound porphyrins as well. And what I found here is that they showed actually like fairly poor fits. So considering that this practice is one of the commonly employed in the like electron transfer study to identify that there is a like driving force dependent electron transfer rate by fitting like decay rates of one surface mount molecule paired with different donor molecules. But it seems that this practice is invalid in our system. So we needed to try it in other way. So what we did is to fit the Marcus equation to exactly the same plot, but in a different point. So we fit one of the like cobalt complexes employed, but paired with 4 different porphyrins. And in this case, interestingly, the fitting was much better. And more interestingly, the cobalt complex, which is unsubstituted BP molecule, showed the fastest electronic coupling value. And that is actually, as compared to the like simply dimethyl structured cobalt complexes, more than two times a higher value. And considering that the Marcus equation describes that electron transfer rate is proportional to the like square of electronic coupling, so that in this like 2.5 times difference is going to be larger, for example, up to 6 times when it comes to electron transfer rate. So we needed to find out the reason why the coupling changes over the similarly structured cobalt complexes, so that we did some calculations. First of all, the distance between the donor molecules and the surface bound acceptor molecules was calculated using single point energy calculation. And the van der Waals distance between the 2 molecules was shown to be 3.5 angstrom. And we also calculated the molecular radius based on the calculated volume. So here in the table, it shows the cobalt complexes including this work have different molecular radius. So we thought this might be, the difference in electronic coupling might be attributed to the difference in size. So we set a model, which is like this electronic coupling is probably donor acceptor distance dependence. So the like distance between the porphyrin plane to the core of the cobalt complex is shown as RDA, and any additional distance, which is shown to be the red box in this slide, are the length of the substituent substituted on the ligand structure. So that gives delta R, which gives additional distance to the core. So we did, we plotted the HDA value, which is electronic coupling out of the fitting in the previous slide, as a function of the RDA, which is donor acceptor distance, and calculate this tunneling attenuation factor, which is 0.18 in our case. So essentially, if this slope going more steeper, in that case, the electronic coupling is more strongly dependent on donor acceptor distance. But if it goes more flat, in that case, the electronic coupling is less donor-acceptor distance dependent, which means maybe there are like very low physical tunneling barrier or very high electronic coupling. So we did some literature to see whether our value is sort of like reasonable, and found that the donor acceptor like bridged by like pi conjugated bridge shows almost the same trend as our results. So that, and that is actually in solution. So our case, we concluded that this dependence in electron coupling is donor acceptor, the difference in electron coupling is donor acceptor distance dependent electron transfer. But it's not like completely bridged by a molecule, but half bridged, because any of substituent attached to the mediator side is connected through the sigma bond. So back to the initial like hypothesis, whether the electrostatic interaction change the electronic coupling or not, we did some normalization, because this previous fitting on the like, porphyrin side wasn't really good. And that is because of the different electronic coupling on the like cobalt mediator side. So that further decreases down the electron transfer rate measured. So we did some normalization by multiplying the coupling value ratio between the different cobalt mediators, and the result of normalization like tells us maybe this system, these 4 different surface bound porphyrin molecules show pretty identical driving force dependent electron transfer rate. However, it is well documented that the zinc ion can make a 5th coordination with some axial ligand in solution if there is some ligands, free ligands dissolved in solution. But in our case, that's not the case. But we've got fairly polar solvent molecules, which is acetonitrile, having like 37.5 dielectric constant. So that may be make some 5th coordination with zinc, so screen the electrostatic interaction effect. So we changed that solvent into a much less polar solvent, which is dimethoxyethane with 7.2 dielectric constant. And what we found by comparing free base GD2 to GD2, it showed a 7-fold increased the transient absorption decay rate, which means in less polar solvent system, this kind of electrostatic interaction may play a role to change electronic coupling and charge transfer rates. So the conclusion is that we quite often change the electronic structure of the redox active molecule by attaching some simple molecular methyl groups or tertiary butyl groups or whatever. But it changes not only the electronic structure, but also some electronic coupling that might significantly affect like as delta G does. So in the viewpoint of like design the molecule, we need to consider a structural moiety that doesn't decrease the electronic coupling, but actually increases the electronic coupling, hence charge transfer rates. So this is the end of my talk, and I would like to special thank to my supervisor Attila and Peter for their supervision, and Pavel for synthesis of the compounds, and some of our collaborators, Shogomori from Japan, and the Keith Gordon and Joseph from New Zealand for their DFT calculations, and like Andrew and other lab mates for their help in the lab. So thank you, and I'm happy to answer some questions if any.
Thank you very much. So if you would like to ask a question, please, you just need to unmute yourself and go ahead.
I'll kick off with a question. So thank you very much, Inseong, for your presentation. It's much appreciated. It's nice to see some porphyrins. It takes me back many years. So I guess I've got a couple of questions, and they're sort of related. The first question is, do you know what the density of your porphyrins are on the surface of your electrode?
Mm-hmm. Yes, I actually didn't really measure it. I tried to measure it actually by dissolving, first of all, the porphyrin molecules from the TiO2 surface that I used for the electrode, using basic solution, and then did some like spectroscopic measurements.
Mm-hmm.
And then so there are some cases like one porphyrin could be standing up like this, and the other case is porphyrin is like completely lying down like this. And we calculate the dimension of the porphyrins and then estimate how it covers the surface of the TiO2. And we conclude that it's not like stand up like this, and then it doesn't lie on the surface like this, but somewhere in between, for example, like 45 degree. So basically what we concluded is this porphyrin plane is pretty much open to the electrolyte side, so that it kind of it makes it easy for the cobalt complexes to access to the porphyrin plane, so that make the electron transfer fast.
Okay. No, I mean that's a good explanation and answer, because the second part of my question was, you know, if it's sitting up like this on the surface, then the cobalt can't actually get to the face of the porphyrin. Yeah. But the fact you've just explained, it's sitting at 45 degrees, and so in fact it can actually come down and interact with it. I do have some other questions, but I'll let other people ask questions if they have some.
I'll have a quick one. I was curious, so those calculations, you said they were single point energy, but then how did you get to the initial geometry? Because they're perfectly face on like that, and then you modify the distance, but did you previously determine that is the most preferred orientation, or?
Actually, I'm not very expert on that, like depth calculation and those things, but yeah, they pretty much like assume like they are approaching from the like this plane side to the porphyrin. So by changing the distance between the two molecules, they got like that energy dependence on like distance. If it's the right answer for your question, not sure.
Yeah, okay, because I assume that in the film you can find all sorts of orientations and
yeah. I assume they set a certain orientation and then calculate based on that. Yeah.
Thanks.
Of course. Any questions?
I've got another question.
Yeah.
So if I understood the mechanism correctly, what you hope is that the electron goes from your cobalt complex onto the porphyrin, and then from the porphyrin to the electrode. Is that correct?
Yeah, like in terms of order, like essentially when like this is like photo derived driven like electron transfer. So basically we excite the porphyrin that injects electron into the TiO2, and then makes a like oxidized porphyrin on the surface. In that case, there is an electron transfer between donor and acceptor.
Oh, okay. So it's essentially what's happening in the solar cell.
Yeah.
So yeah. Okay. Right. Yeah. So I misunderstood that, because one of your figures had essentially the porphyrin cobalt electron going to the porphyrin, and then but the porphyrin is oxidized to start with. It's effectively photoexcited. It's transferred its electron. And so it's then the radical cation that you're reducing with the cobalt. Because if the order was the other way around, then my question was, well, what gets excited, and why didn't you go for a copper porphyrin or a nickel porphyrin instead? But you've answered the question, so I understand now. Thank you very much.
Thanks.
Were there any other questions?
Yes, I have a little bit of generic question, if I may ask.
Yeah, please.
Yeah, sure.
I would like you to educate me a little bit about electronic coupling, if possible. So,
yeah.
What is the electronic coupling sort of? It's like, is there like a specific physical parameter with the unit that you can describe electronic coupling?
Electronic coupling's unit is actually electron volt can be like calculated by some equations. So
is it an energy difference between like a Fermi level of chemical potential difference or something?
It's more like dependent on how like molecular orbital like meet to each other between the donor and acceptor molecules, so that it could be like affected by the distance, but also how the molecular orbitals are, the shape of the molecular orbitals, so that in that sense, if you use like in the same distance, more pi like conjugated but bulky molecules, in the case electronic coupling value could be increased. So basically, affects.
The larger the electron volt number, the stronger going to be the faster they're going to be the transfer rate.
Sorry, say that again, please. Sorry.
So the higher the difference in electron volts.
That is more on the driving force, which is the energy difference, basically the energy difference between the molecules. So that is a bit different parameters from that. We like distinguish that parameters from electronic coupling. So that is more on the driving force for the reaction.
Okay, so it's a driving force, not the same as electronic coupling.
No, that's different.
So how do they differ actually fundamentally?
Even though like the energy level stays the same based on their geometries and how they get close to each other, that sort of things also affect the electronic coupling level. So that is they should be different from like one to another.
Okay, and so the important parameter for you is to know, is that the rate of electron transfer or efficiency of some sort, like quantum efficiency of some sort? Or is this, which one parameter are you mainly after?
Actually, not really. At this work, I'm not really interested in any like photo conversion efficiency and that sort of things for the like whatever performance for the devices. But here, what I need to know is how these kind of parameters affect the electron transfer rate for those kind of like further information for the device like development and molecular design, and that point of view. Not really interested in the device like performance and then sort of things related to some efficiencies.
So when you say that the rate is important, means that the quenching rate, right? The electron quenching rate.
Yeah. The rate is what I'm interested in, and then what factors affect that rate is what I need to look at.
Yeah. Okay. Thank you.
All right. I think probably in the interest of time, I think we might have to stop the questions there. So thank you very much, Inseong. That was a very interesting presentation. So again, kind of virtual round of applause from everybody here, I'm sure.